All right, hello everyone. So today I'm going to be presenting to you the work that I did on the effectiveness of bisection debugging when applied to the specific problem of localizing software performance regressions. This is a study that I conducted in SAP Vancouver as part of the P&R team, or the Performance and Reliability team. And this was recently published as a journal paper in the Empirical Software Engineering Journal, or EMSE. All right, so just to kick things off a little bit and give some context to everyone, let's say that we're trying to test a web application and we're trying to test the logon functionality and how performant it is, so how quickly it can respond and go to the home page so that it can log on. So first, we're going to try to test out yesterday's version of the application and see how it goes. All right, so now it's typing the usual user input. And then in the secondary, you're going to see the time. And then in this case, it's 2.43 seconds. So from pressing the sign in button up to when it shows the logon successful screen, it took around 2.43 seconds for its response time. So now let's take a look at what happens in today's version of the application. So this is the same application, but it's a different version of it after a few changes. Okay, so the same user interactions as before. Okay, so in this case, instead of 2.43 seconds, it actually takes 3.27 seconds instead. So there's been an 800 millisecond regression between those two versions that we just tested. So this slide gives you a bit of a summary of what we just saw. So essentially on the left side there, we have the good commit. So that's the commit that this one right here is the commit that we just tested first. And it took 2.43 seconds. And then there's the bad commit, that's today's version, and it took 3.27 seconds. And then in between those two commits, there's a bunch of other commits that are untested. Okay, so in this case, our goal is to localize exactly where that regression is coming from. So we see that there's been an 800 millisecond increase in the response time. So we have to figure out precisely, which of these untested commits might have introduced the regression, or perhaps it's even the last commit itself. And this problem is called localization. So essentially, we want to localize or find the root cause of the regression that we just saw. So there's many different techniques that people use to localize regressions, in particular software performance regressions. So you can see 4 of them here. So we have code analysis, there's profiling or logging, so adding some logs to the code and instrumenting it. And then there's also call tree or timeline analysis. You can even say that call stack analysis falls under this umbrella. But the main technique that we're going to be focusing on for this presentation is bisection. Okay, so bisection debugging. Okay, so what is bisection? So for those of you not familiar with this term, it's basically a technique that allows you to efficiently localize the root cause or find the commit that introduced a certain regression. So let's say that we start off with this set of commits here on the top. So again, we have the good commit on the left side and then the bad commit on the right side. The way that bisection works is we start by testing out the middle commit. So it's this one over here. And then based on the result in the middle commit, whether it's good or bad, we either take the left side or the right side of the search space and reduce the search space just to that portion. Okay, so in this example here, the middle commit ended up being a bad commit. So what we do is we take the left side of the search space, because that means that every commit after the bad commit, or like after the middle commit, would also be bad, assuming that everything is monotonic. So what we do is we take the left side, and then we basically just proceed recursively. So let's take the middle commit again, and in this case, it's a good commit. So we take the right side this time around, and then we do the same thing here. And in this case, the middle commit is a bad commit, and this is the last one that we're going to be testing because there's nothing else to test. And in this case, this is actually the root cause of the regression, because this is the very first commit in which the bad commit manifests itself. Okay, so this is what we consider the root cause. Okay, so what we just talked about there is something that's applicable to any type of regression, whether it's functional or performance. But for this study, I'm focusing particularly on performance regressions. So how is that different from functional regressions? There's a lot of similarities that's involved, but in this case, the way that it's different is that instead of just checking whether a certain commit is good or bad, or whether it's correct or incorrect, we actually need to compare the performance result according to some baseline value. Okay, so we call that the bisection metric. So just to give you sort of this simple example here, let's say that we have, again, it's the exact same blocks that we saw from earlier, except it's replaced with numbers. So let's say that the good commit, for that one, it took 2.5 seconds for the screen, let's say, to respond, or for the application to respond. Whereas for the bad commit, it took 4 seconds. So there's been this 1.5 second regression. And in this case, let's say that anything that's above 3 seconds is considered a bad commit. So that's what we call the baseline value. So again, as before, what we do is we go to the middle commit, and then we're going to get some performance result. In this case, it's 3.9. So 3.9 is greater than the baseline value. So therefore, we consider this as a bad commit. And then we essentially just proceed as before, right? So we take the left side, and then we take the right side based on the result from this middle commit here. And we get the same root cause block as before. Okay, so this is what we consider as the culprit, or the block or the commit that introduced the regression. So as you can see, it's very, very similar, except in this case, we're actually just comparing with some sort of baseline value. Okay. So bisection is actually something that's used very commonly in practice, both for functional and performance regressions. But here I'm going to present to you some of the pros and cons for using bisection for performance regressions in particular, because that's the main topic of the paper. Okay, so one of the main advantages of bisection is that it's minimally intrusive. So what that means is that there's often no instrumentation that's required. For a lot of the other techniques that we mentioned earlier, like for example, for call tree analysis, for those, usually you have to instrument the code in some way. So it's going to introduce a little bit of overhead in the performance, right? Whereas if we want to test out the performance, we want as little of that overhead as possible. So with bisection, you don't have to include any of that instrumentation. So therefore, the overhead itself is minimized. So that's a good thing. The other advantage is that human effort is reduced to validation only. Because usually when you're trying to localize a certain regression, you need to do a search first. So you need to search for the commit or the root cause, whatever granularity that is. And then you need to validate whether the commit that you just found is actually the root cause, doing some, maybe some reverts, some cherry picks and all of that. But in this case, since the bisection is basically going to be doing the search for you, the only human effort that's required here is the validation. So it makes it a little bit simpler in that regard. And then the last advantage is that it's very simple and very intuitive. It's essentially an application of binary search into the problem of localization. And binary search obviously is something that's learned by a lot of software engineers early on in their careers, something that they understand very easily. And therefore, the output itself is something that's very easy to understand. But there are some disadvantages, some cons that we need to consider as well. So one very important con is that the performance results are very noisy. So for functional bisection, usually, again, it's just a matter of whether it's correct or incorrect. You want to test whether it's, passing the test, or maybe it's not passing the test. But in this case, since we're dealing with comparisons, greater than or less than, it's not just a binary metric that we have to consider here. It's more of a sort of a continuous variable that we have here, and it's based off of some performance distribution. So performance results are very noisy. There's a high variance, and that's going to affect your bisection. The other disadvantage, rather, which kind of relates to the previous disadvantage, is that unlike functional regressions, the results in the commit range are almost guaranteed to be non-monotonic. So instead of you having that sort of step function as before, where everything before the root cause is a good commit and then everything after the root cause is a bad commit, in this case, that's not necessarily the case because of the variance that's involved. So maybe you have like an up and down type of behavior in your commits. And then the last disadvantage is that performance regression tests can take a very long time to execute. And again, this is something that sort of feeds off of the very first disadvantage here, because since you have very noisy results, oftentimes you need to make sure that you have multiple iterations of the same metric when you're trying to get the results for the same metric. So because of those multiple iterations, that means you take more time to actually get your numbers. So that's one of the cons. Okay, so what's the impact of the cons that we just discussed? Well, first of all, since performance results are noisy, as I just said, what that basically means is that bisecting performance regressions doesn't have any correctness guarantees. So it's possible that when you run the bisection on a performance regression, you're going to get some sort of bogus result because maybe the performance numbers maybe are too close to the baseline. So they ended up taking the wrong path in that case. So that's one of the possibilities that you might encounter. And therefore, since performance regression bisection often has long execution times, as you can see here, bisections providing incorrect results can be very, very costly. So, we want to make sure as much as possible that the bisection that we run is something that's most likely going to give us the correct result. So we want to sort of maximize that possibility, that probability that we're going to get the correct result, right? So again, based on these observations, it would be useful to, as it says here, first of all, identify and analyze the properties that contribute to a successful bisection, as I just mentioned. So in this study, I'm calling these the contributing properties. So what are the inputs? What are the properties that contribute to a successful bisection? Some bisection that would that most likely will succeed. And the other question that we want to ask or that we want to understand is what these contributing properties look like in real world performance regressions. So what are these contributing properties like in practice? Okay, so these are the overarching goals basically of the entire study, as we want to answer these two questions or address these two goals. So for the first one, for identifying and analyzing the properties, the contributing properties, the main strategy that I've employed is I've first of all derived what's called an effectiveness measure. So what this effectiveness measure does is it basically tries to quantify how effective bisection is going to be. So what's the likelihood or what's the probability that this bisection, given these inputs, these properties, would succeed? Okay, and based on that effectiveness measure, I've conducted a sensitivity analysis on each of those contributing properties. Okay, just to see, what effect do each of these properties individually have. For the second one, the strategy that I've employed is I've collected over 300, so in this case, 310 software performance regression bug reports. And I performed a qualitative and quantitative analysis on each one of these. Okay, so in this case, I've classified the bug reports, as you can see here, based on the information that's provided, so that we can assess their suitability for an effective bisection. Okay, and one of the other things that I tried to do is identify any information gaps that might be present in these bug reports, because if we're lacking information regarding the what the regression looks like, then in that case, we won't have the means to effectively analyze whether the bisection is actually going to succeed or not. So that's one of the things that I try to sort of answer and analyze in this study. Okay, so that's the main goal that we have here, and then this is the strategy that I've laid out. Okay, so let's start with the effectiveness measure and the sort of derivation of that. So I'm not actually going to go through all of the derivation here in this presentation because that's something that you can read yourself in the paper. But in this case, there's actually two main intuitions that I want to start off with. So the first observation is that the effectiveness measure should represent the probability that the bisection gives us the correct answer. So this is pretty obvious, right? So we want, what are the odds? What's the likelihood that this effectiveness measure or that this bisection is going to give me the correct result? Okay, so that's our main goal. Okay. But in this case, it's a little bit of an ambiguous statement, right? So for example, what does it mean when we say bisection gives us the correct answer? What does that even mean? So to answer this, one of the observations that we need to make is that the performance of the good and bad builds can be modeled as probabilistic distributions. So in this case, it doesn't even matter what kind of distribution it is at this point. The only thing that we care about is that it's some sort of distribution. And a regression is considered to have happened if some aggregate measure of that distribution shifted in some way. So let's say it's the mean or the median, maybe the mean increased, maybe the median increased. So that's the sort of definition that we have when we say that bisection or the regression has happened. Okay. So if you put these two observations together, we can kind of come up with this informal definition for the effectiveness. So the way that we can define it informally is it's the probability that the first commit in the array of commits where the distribution shifts is commit C, given that bisection output C. Okay, so given that the bisection algorithm output this commit C, so it tells you this is the answer. What's the probability that the answer that bisect gives you is actually correct? What's the probability that there actually was a shift at commit C? Okay, so if we kind of translate that into probability notation, it's going to look something like this. So this symbol right here, this epsilon x comma C is effectiveness. And then this portion right here, the dx equals C, this is what basically says distribution shifts at commit C. So that's the expression that corresponds to that. And then this conditional here is bisection output commit C. So B is basically the bisection algorithm. So this is basically just a mathematical translation of this informal definition here. Okay, and if we want to expand that using Bayes' law, it's going to look something like this. So it's going to have these three different components here. And I've actually named each of these components. So in the top portion here in the numerator, so you have the likelihood, okay, which is essentially just the inverse of this guy here. And then you have the shift probability. So what's the probability that the distribution shifts at commit C without any conditions? And then at the bottom here, you have the output probability. So what's the probability that the bisect algorithm outputs C? So this is very typical, stuff. So this is just an application of Bayes' law, essentially. Okay, and once you sort of go through the motions, you are going to be able to derive each of those components, those three components. So you have the likelihood here represented by lambda, the shift probability represented by sigma, and then the output probability represented by omega. So I'm not going to go through the entire derivation here because it's a little bit tedious to go through that here, but that's something that you can refer to the paper for. Okay, so based on the effectiveness measure, there's certain inputs that would contribute to the effectiveness, to the value of the effectiveness. And these are the four inputs that, that would be considered as the contributing properties. So the first one is the baseline. So this is the value that each middle result is compared against. So if you remember that example that we had, where we had 2.5 versus 4, the baseline that we used was 3 seconds, right? So all the results in the middle commits that we gather, we're going to compare that with the baseline to see which path we're going to take. So this is one of the, this baseline value is one of the properties that would contribute to the effectiveness, okay, based on the effectiveness algorithm or the equation. Another one is the distributions. So this is the probability distributions that describe the performance of both the good build and the bad build. So again, in this case, we're just talking about this more generally. So it could be any distribution really. And then the other one is the length of the commit range. So if you have the good build and the bad build, how many commits are there in between, including those two builds? Okay. And then the last one is the transition index. So this is basically the index of the commit at which the distribution shifts. Okay, so what's the distribution shift index essentially? So one thing to note is that for this study, for the distributions, there's actually 3 types of distributions that I've considered. So those are normal, log normal, and Pareto. So these are the main ones that I'm going to be using in the study, and I've derived these distributions based on the mean and the standard deviation. Okay. The reason why we're using log normal and Pareto is that these are both heavy tail distributions. And a lot of previous studies have shown that these distributions appear in realistic workloads. So this is one of the reasons why we have this here as well. All right, so again, these are the 2 goals that I showed earlier, and I have all the research questions that I've answered in the paper. The way that I've structured it is basically for the odd numbered research questions, these ones would sort of feed into this goal right here of analyzing the contributing properties. And then for all the even numbered research questions plus RQ9, these are more the realistic types of questions where it tries to analyze what the contributing properties look like in practice. But for the purposes of this presentation, because we don't have a lot of time, I'm only going to be going over these 5 research questions here. Okay, and you can read the rest of the results in the paper as usual. Okay, so let's start with RQ1. So what impact does the choice of baseline have on the effectiveness? Okay, so what I did here is that I graphed the baseline value ranging from the mean of the good build to the mean of the bad build. And then I essentially just plotted the effectiveness going from within that range. Okay, so a typical graph would look something like this, where you have something that increases monotonically, and then it reaches some sort of peak, and then after it reaches the peak, it goes down. So this is the typical pattern that you would see in these baseline graphs. Okay, and in this case, the peak, the X value for that is what we call the optimal baseline. So this is essentially the baseline at which the effectiveness is the highest. Okay, and in this case, the optimal baseline is somewhere around here. So it's a little bit closer to the mean of the bad build in this particular example here. Okay, this isn't too surprising because obviously if you try to use the mean of the good build as the baseline, you're obviously going to have a fairly low effectiveness because if you think of it in terms of a normal distribution, you're essentially just having it, right? So you're basically going at the very half, and you're kind of just going 50-50 in terms of whether you're going to go below the mean or above the mean, especially if it's the good case. So that intuitively tells you that it's not a very good baseline to use. Okay, so one of the other questions that I tried to answer for this RQ is I tried to compare the normal distribution with the log normal and the Pareto distributions. And what I did here specifically is I tried to use the optimal baseline that's computed for the normal distribution. And then I tried to see what the effectiveness is going to be if the distribution actually had been log normal or Pareto. Okay. And in this case, you can see that the average or the effectiveness is actually not too far off on average. So if you look at this first row right here, for example, what this is basically saying is that in the log normal case, if we were to use the normal or the optimal baseline for the normal case, it's only about 1.03% off in terms of effectiveness. And then for Pareto, it's only about 7.29% off, which is a little bit more significant, but it's still not too bad. It's less than 10%. Okay. So on average, it's actually not too far off. Having said that, of course, there's drastic differences in some cases. Like for example, in some cases for Pareto, especially, there's instances where it's greater than 20 percentage points off. So in those cases, it's not necessarily the exact same as what you would see in normal. But the main point that I wanted to make here is that normal distributions can be used as a sort of rough estimator to determine the effectiveness in the absence of distribution data. So this is useful because a lot of the times when you receive a bug report, the user is not going to tell you, these are the raw results, or this is the distribution of the performance results that I got. A lot of the times they won't even tell you what they won't even actually do a proper test, right? They're just going to tell you, oh, I ran it once or maybe a couple times, and these are the numbers that I got. So if we were to only use those aggregate numbers, at least we're able to estimate what the distribution is going to be if we were to just use the normal distribution. Okay. So that's for RQ1. The next research question is RQ2. So do real-world performance regression bug reports provide enough information to assess a proper baseline value? Okay, so this is the baselines in practice research question. And in this case, what I found out is that only around 10% of the bug reports that we collected or that I collected provided all of the information that's needed. So that means only 10% provided both the full distribution, that means the mean and the SD, and the full range of commits. Okay, so if you look at the sort of breakdown here, most of the time, the reason why it's not fully provided is because most people, even though a lot of them provide the version information, the vast majority of people don't provide the distribution information. So they would basically just only tell you the commit range for the most part, but in most cases, they won't tell you what the distribution information is. Okay. And, this is understandable, but at the same time concerning, right? Because what that basically means is that you're not able to fully compute the effectiveness, because these are some of the important properties that you need in order to compute the effectiveness. Okay, so what are some of the measures that we can take to sort of fill this information gap? So on one hand, you can do some preemptive measures. So for example, one of the recommendations that I included in the paper is to include a bug report template, which essentially forces the user to fill in certain parts of the bug report or certain information in the bug report. And then the other preemptive measure is to provide easy to use test commands. So for example, maybe there's certain test commands that the user can use. Maybe it's just like a button that the user can press. And then once that button is pressed, then it's going to spit out, certain distribution information for a specific workflow. So that's something that the user can kind of automatically just put into the bug report, and it's going to make it much, much easier for the developer to see. And then the other measures would be the post facto measures. So one would be performing baseline reruns on different hardware. So this is essentially just going to reestablish what the distribution is going to be. And it essentially just fills in that information that was lacking in the bug report to begin with, the distribution information. And then the other post facto measure would be rough estimators for effectiveness. So for example, maybe we can use certain measures that are not necessarily what corresponding to the information that we have, but would nonetheless estimate the effectiveness value. Okay. All right, so the next one is the impact of the distribution. So what impact did the distributions have on the effectiveness? Okay, so one thing to note first is that the individual impacts of the means and the SDs are also reported on the paper, but I'm not going to go through all of those here. For this presentation, I'm going to focus exclusively on what we call the overlapping coefficient. Okay, so the overlapping coefficient is basically the region of overlap, or the percentage of overlap between two different distributions. Okay, so as it says here, the higher the overlapping coefficient is, the larger the percentage of overlap is between the two distributions. And what we care about here is the overlapping coefficient between the good distribution and the bad distribution. Okay, So what I basically did was I performed a correlation analysis on the overlapping coefficient and the effectiveness. And in this case, what I found is that there's a fairly significant negative correlation between the effectiveness and the overlapping coefficient. So in this case, the Pearson value is negative 0.4799. Okay. So what this basically indicates is that the overlapping coefficient can be used again as a rough predictor of effectiveness. And this is one of the things that you can use, especially in cases where there's no commit range data that's provided to you by the user. So let's say that the distribution is provided to you, but the versions or the hashes are not provided to you, the commit range. So in that case, you can kind of use the overlapping coefficient as an estimator. Okay. And this also provides the context for the next research question, which is as follows. So how close or far apart are the pre-regression distribution X and the post-regression distribution Y? So the good distribution X and the bad distribution Y. How far apart or close are they from each other in real-world performance regressions? Okay. And in this case, the result that I got is that as summarized in this graph right here. So as you can see here, distributions provided in real-world regressions tend to have small overlap, making them more amenable to bisection. So in this case, as you can see, the vast majority of the distributions fall within the 0 to 5% range of overlap. Okay, so based off of the results that we got from the previous slide, this seems to indicate that most of the real-world regressions are pretty amenable to bisection. Okay, and then the last research question that we're going to go through here is how effective will bisection be when applied to real-world performance regressions? And what I did here is that I took account of all the successful and failed bisections that we ran in our team, the PNR team. And this is sort of the summary of that. This is extrapolated results because there's actually only 40 bisections that we conducted over the certain time period that I was looking at. And then I extrapolated it based on a few additional information that I described in the paper. So in this case, you can see that it actually correlates pretty well with what we expect. So for example, here, if the effectiveness is between 0% and 25%, the vast majority of the bisections fail, right? So 50 out of 60 of them fail, okay? If the effectiveness is between 25 and 50%, it's the same thing. So the majority of them also fails, but not to the same extent as the 0 to 25%, okay? And then once you go from 50% to 75%, the majority of them passes, they succeed. And that's even more so the case for 75% to 100%. So in this case, 213 bisections succeeded, but only 3 failed. So what this basically indicates is that the effectiveness measure that we derived from earlier is a good indicator of what the actual effectiveness is of the bisection in the real world. Okay, so these are the recommendations that I've included. And again, I've summarized all of these in the paper as well. We already talked about these last 2 here at the bottom. The other 3 are implementing a mechanism to find the best bisection metric. So again, it's important for us to figure out exactly what metric is going to maximize the chances of us having a successful bisection. And we can take advantage of the effectiveness measure that I've derived to make that assessment. The other recommendation is computing the effectiveness before and after the bisection. This one's actually kind of related to one of the research questions that I didn't go through here, which is on the transition index. So you can refer to the paper for that one. And then the other recommendation that I have here is using variance of performance regression bisection, depending on the values of the contributing properties. So perhaps in your specific scenario, you care more about the accuracy of the bisection because your distributions are so close to each other. So in that case, you might consider using something like noisy binary search, which is something that's fairly well studied. On the other hand, if your distributions are far enough from each other and you care more about the speed of your bisection, then you probably want to focus your attention on minimizing the number of commits or number of tests that you want to, or number of commits that you want to test. So in that case, you can consider using something like selective debugging to minimize the time or the execution time. Okay, so there's a few threats to validity or limitations in this study. So the first one is that the commit range has been modeled as an array. More generally speaking, you can model the commit range as a DAG. So it's a directed acyclic graph. Because as you guys know, if there's if you have commits, usually there's branches that are involved and merges. So in that case, it's more generally a DAG as opposed to an array. However, from the standpoint of effectiveness analysis, an array seems to be suitable. So we can basically just do a topological sorting of the DAG, and it's gonna mesh pretty well with what we would expect from an array. The other limitation is that there's a limited number of bug reports that has been analyzed. But one thing to note is that this number is fairly comparable to previous bug report studies that have been conducted, including one that I conducted on JavaScript bugs in web applications back in 2016. And then the last one that I've written here is that the one at a time sensitivity analysis that I've conducted, it only captures the individual contributions of each property, but it doesn't capture the interactions between those properties. So it doesn't know any of the sort of correlations between those properties. So this is less of a limitation, or it's less of a threat to validity and more of a sort of limitation in terms of what we didn't conduct. Okay, so just to sort of summarize what I just discussed here. So we went through what bisection is and how bisection can be used in terms of trying to localize performance regressions. And then I described the overarching goals of the research. So basically trying to analyze the contributing properties and how they appear in practice. We went through some of the results, in particular for the baselines and the distributions, and also how effective the effectiveness measure is in terms of trying to predict whether a bisection is actually going to succeed or not. And then I gave some recommendations on what developers can use so that they can better assess whether to use bisection in their specific scenario, and also to come up with better means to increase the chances of their bisection being successful. Okay. So that concludes my presentation. Thank you.